So as we look at this equation, so what type of reaction is this? Well, this is AB plus CD. And so that means this is a double replacement reaction. So that's going to be the calcium reacting with the phosphate and the potassium reacting with the nitrate. So now the potassium will form KNO3, all right, +1 and -1. So that's balanced out there. This is aqueous because all nitrates are aqueous. That's the solubility rules. We talked about that the other day. And I need to go look at that activity too that you guys posted to see what y'all have put on there. Now we look at the last one here. Calcium is going to react with the phosphate. I'm going to bring the charges over. Now these charges are not balanced, so that we're going to have to balance this formula out. So the common number between 2 and 3 is 6. 6 divided by 2 gives me 3 calciums, and then 6 divided by 3 gives me 2 phosphates. So the formula that you would have for this is Ca3PO4 2. Now we go and look at the solubility rules. All phosphates are insoluble except with ammonium and alkali metals. Calcium is not an alkali metal and is not ammonium. Calcium is an alkaline earth metal. That means that this compound is insoluble. So that's a solid. Now, the last thing that we have to do, we need to balance the equation out. So if I look and I see that I've got 3 calciums on the right-hand side and I look at the left, I only have 1, I got to put a 3 in front of that. Now when I put a 3 in front of that, that gives me 6 NO3, so we're going to put a 6 here. And then when I have 6, I'm going to put a 2 in front of the potassium phosphate. That gives you 6 potassiums, 2 phosphates, so now we're balanced, okay? So everything's balanced. What we also see is that the calcium phosphate is a precipitate. So that's going to be precipitating out. So that's going to help us with figuring out the spectator ions. Now, keep in mind that we talked about spectator ions and how we go about writing out the equation. So everything that's aqueous will be broken down into its respective ions. So the first reactant here, you have 3 calcium, 2 plus aqueous plus 6 nitrate aqueous plus 6 potassium. I'm just going left to right. Aqueous plus 2 phosphate aqueous yields 6 potassium aqueous plus 6 NO3 minus aqueous. You still have to keep in your balanced equation plus calcium phosphate. And this is a solid. So remember, yes, the other day I talked to you about how you figure out the common terms on each side, which ones are the same, and you cross them out. So potassium and nitrate, potassium and nitrate are like terms, so they get crossed off. Now, in doing so, that also answers this question here. That answers this question about, which is their spectator ions. All right, so that's how you figure that out. Now, bring everything else down to this next blank. So you got 3 calciums plus 2 phosphates yields calcium phosphate. And that's a solid. So that's your answer for letter C. So as you do this balanced, the net equation up on top, you cancel out like terms and you bring the rest down, and that is what reaction you're going to observe in solution. Are there any questions with that? All right. So moving forward here then. this is just a couple slides that explains that. We talked about acids before, and acids are compounds that contain hydrogen. So these are just some different acids. These are 7 of the strong acids that are lit on your things I should know list. Remember that acids are, in our case, they're strong acids, so they're going to react with anything that's a base. So bases include your alkali metals. So we did talk about this the other day, but I'm just going to remind ourselves. So sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, lithium hydroxide, and you got calcium hydroxide, strontium hydroxide, and then you have barium hydroxide, just so we have that complete. So there are 8 strong bases, and they all contain hydroxides. So typically, when you see a hydroxide, you're going to think of basic compound, but there are 8 of them that are strong. Here they are. All right. So I'm going to move on if y'all don't have any questions. The reason why we do that is because of neutralization. We've already talked about neutralization, so we're going to move on from that. There's your example. Now, gas forming reactions, and we didn't get to finish this the other day, so I want to finish this out, and then we'll start our redox reaction. So gas forming is where you produce a gas as a product. And a good example is where you have H2CO3. I think this right here. Yeah, so H2CO3 is our carbonic acid. Sometimes a reaction will do a double replacement reaction, and it'll form carbonic acid. Now, what it doesn't show you is the fact that carbonic acid does break down to form water in the liquid phase plus CO2, which is a gas phase. So anytime you see a product here, so let's say for example like this, so we react the calcium with the chlorine to form calcium chloride, and then the hydrogen reacts with the CO3. Now hydrogen is +1 and CO3 is 2-. So in order for this to balance out, you're going to have 2 hydrogens. All right. And so when you do that, knowing that this is in solution, this is carbonic acid. So anytime you have a compound like this, that compound is actually going to break down into H2O liquid plus CO2 gas. If you've ever taken vinegar and you put vinegar and baking soda together, you get a fizzing action to take place. What's happening is when you put baking soda and vinegar together, that is a neutralization reaction. But one of the products that's formed in that reaction is carbonic acid. And the carbonic acid breaks down to form carbon dioxide. And that's where the fizziness comes from. That's why you get all those bubbles. That's why we do use it as a volcano demo. And I know y'all seen this before at some point in time. So anytime you see this, now on your things I should know handout, there are 3 different reactions, all right? And in fact, I'm going to pull this up right fast here. So the things I should know handout, let's find it here. I'm pretty sure I've got it somewhere here. How many of you have your things I should know handout present? All right. So when you look at your things I should know handout, you get these 3 reactions. Anytime you see carbonic acid, sulfurous acid, or ammonium hydroxide, any one of those 3, you automatically know that they break down to these. So if I were you, if I would take a picture of this, or I would put a star beside this, because that's an important detail. That detail can make the difference between you getting a question right versus wrong. And going back to that PowerPoint slide, that slide, there it is. So that's this slide that we're working with. This compound is, described to you on the things I should know handout. So keep in mind that, all right? Single replacement reactions. So before I get into talking about oxidation reduction, so single replacement reactions. The generic formula for this is AB plus C yields AC plus B. If you notice that what's happening here is B and C are flipping places. So you can see what's happened there is that B and C are basically switching. That's why we call it single replacement reactions. So that's the generic formula. Now, I want to also show you on Moodle that, and I talked to you guys about this the other day, but I wanted to show you again. So on Moodle, you have the reference tables. So I'm going to go ahead and pull this up here. Now, the reference tables is a resource packet that has a lot of information in it. But specifically, what I want you guys to pay attention to is right here. All right, so single replacement. So we have, now I've talked about all the different types of reactions up to this point, and we are into our last type of reaction, which is single replacement. So on this page, it lists the different types of single replacement reactions. So you'll talk about metal to metal, and then we'll talk about halogen replacement. So halide to halide replacement is what we call that. And now what we need is the activity series, okay? So the activity series is found on the next page. And you will want to print this off. So this page you definitely want to print off along with the other page, so page 6 and 7. Now, the activity series is basically it's just based off the activity and how active the element is. So the higher you are up on this chart, the more active you are. So lithium is the most active metal, and then fluorine is the most active non-metal. Now, there's no rhyme or reason for this that you guys need to worry about. What you need to be focused on is the fact that you're going to use the activity series chart to go about answering the problems and figuring out the products. So you're utilizing the activity series along with this, you'll be able to answer any question that's presented to you. Now, along with single replacement reactions and a couple other ones, but for now, we want to talk about reduction and oxidation. Okay, so that's what I want to spend a little bit of time on today. So oxidation is where you have a loss of electrons, and reduction is where you have a gain of electron. So oxidation will make something positive, and reduction is something that will make it negative. And so as we start to look at reactions, more specifically the electrons that are being transferred, we will see that the elements will change in their oxidation state, their oxidation number. So that's where I want to spend a little time at today, is I want to talk to you about how you determine the oxidation state for an element. Now, we'll start with something easy. All right, we'll start with copper oxide. Now, this is something that you have seen already in the previous weeks. And what we do is we need to figure out the charge of the copper. Now, copper here, its charge is really dependent on oxygen. So oxygen is -2. There's only one oxygen. So 1 times -2 gives me -2. What cancels out -2? +2. Now, if you look, there's only one copper So 2 divided by 1 gives me plus 2. So the oxidation state for this copper is plus 2. Now, if I look at just elemental copper by itself, when you have an element that is by itself in its elemental form, the oxidation state is 0. Now, if this was a reaction where this copper 2 oxide was reacting with whatever to form copper, what we would see is that the copper goes from plus 2 to 0. Now, in this case, the copper is gaining 2 electrons because it's going down in positive, so it's lowering the positive charge. So if you increase in positive charge, you're becoming oxidized. If you go down in charge like this is, you're being reduced. All right. Now, this reaction is incomplete. So that means that if copper is reduced, then something else has to be oxidized because the electrons have to come from somewhere. And that's one of our goals that we're going to be doing in this, is that we need to figure out what's oxidized and what's reduced. So that's one example. That's actually 2 examples because of the elemental copper. Another example would be if we have SO4 2-, and we want to figure out the oxidation state for sulfur. So you're saying, well, sulfur, isn't that on the periodic table? And I'm going to say yes. Well, isn't its charge -2? I'm going to say not necessarily. Because these elements can change in their oxidation state. Now, if you have just Na2S like this, now, yeah, so the sulfur is -2 and the oxidation state of sodium is +1. That one's easy. But this is different because it's a polyatomic ion. Polyatomic ions are not normal. They don't have the same oxidation state as what you expected them to have from the periodic table. So how do we go about figuring this out? All right, we know that the overall charge is -2, so we set it equal -2. Oxygen on the periodic table is -2. There's 4 oxygens, so that's a total of -8. Now the question is, what minus 8 equals -2? So in other words, we got to figure out what X is here. So X is 6. And I look at the sulfur and I say, okay, how many sulfurs are in sulfate? There's only 1. So that sulfur is +6. Now, let's say we take a reaction and we go to SO2. So it changes from sulfate to sulfur dioxide. All right, now we look at again, the overall charge, which is 0. So we set this equal to 0. The charge on the oxygen is -2. There are 2 oxygens. 2 times -2 gives me -4. And 4 minus 4 gives me 0. Now there's only 1 sulfur, so that 1 sulfur is going to be +4. So the sulfur changes from +6 to +4. So would you say that's reduced or oxidized? Are y'all even listening to me? All right. Okay. So Grace says reduced. Cassandra says oxidized. All right. So
I
Portia
think it's
says.
oxidized too.
All right. See, it's oxidized. All right. So is it becoming more negative or more positive? What do you think? I asked that just a general question. Is it becoming more negative or is it becoming more positive? What do you think?
Is it becoming more negative?
Yes, right. So if it's becoming more negative, does that mean that you're going to be gaining electrons or losing electrons?
Gaining.
All right, so if you say gaining, which one of the points does that match up to be?
Reduction.
Right. So this was reduced because of that reason. Now, let me give you a short way of remembering it. So, oil rig seems to be people's to go to. How many have heard of oil rig in a different class before? Now,
Can you repeat that?
which part? Oil rig?
Your question.
So who's heard of oil rig before?
Oh, I ain't never heard of that.
I have.
What do you remember what it stands for?
Yeah, I guess oil is losing and oxidation is losing and reduction is gaining.
Exactly. That's how you can remember that. Yeah. So that's an easy way to remember the definition here. So oxidation is lose, reduction is gain. So anytime you're dealing with with a problem like this, you got to figure out the oxidation state. Okay, that is the first thing that you have to do. And so just like we saw in the last couple examples here, the sulfur went from 6 to 4, so it's being reduced. Now, let's see here. Can't erase those. So one other comment here is that one cannot occur without the other. So oxidation has to occur with a reduction. They go together. So now the PowerPoint goes through and talks about how you calculate the oxidation state, kind of like what we just did. And so one thing that you want to make a note of is that elements in their native state are going to have oxidation numbers of 0. So copper was by itself, it was 0. If you have iron solid, it's 0. If you have hydrogen gas, it's 0. So these are all in elemental states. Remember, there are 7 diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, bromine, and iodine. So any of those in their elemental state will be 0. If you have sodium by itself, it's 0. Now, sodium solid reacts with chlorine to produce 2 NaCl. So we look at this reaction and I say, okay, what element is reduced? What element was oxidized? So what we do is we look at the oxidation state, and I was trying to change my color, but I can't. So sodium is 0 and chlorine is 0 because they're by themselves, they're elemental. Now we go over here and we look at the sodium and then we look at the chlorine. Now chlorine is -1 because that's from the periodic table, and then sodium is +1 as that is also from the periodic table. So I look at sodium, and sodium goes from 0 to +1, and chlorine goes from 0 to -1. Now, let's look at sodium. What do you think sodium has done? Reduced or oxidized?
Oxidized.
Right. So it's oxidized because it's become more positive, right? So what does that mean chlorine has been?
Reduced.
Yeah. Portia, does that make sense?
Yeah.
All right. Are there any questions with that?
No.
On the other one, like with the sulfur, how did you get the 6? Like the 6 minus 8? Or
Okay,
I know
so
you got the 8 from like 2 times 4 because there were
okay,
4
all right.
oxygen atoms, but
So all you gotta do
Other
is
one?
so you just gotta figure out x. All right, so x minus 8. So just type in your calculator what minus 8 equals -2. It's 6.
so, yeah, but like where did like how like is the -2 like the charge for oxygen?
No, 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 no. So sulfate is SO4 with a -2 charge. So that's the overall charge.
Oh,
So
okay, gotcha.
so that's why I set this equal to -2.
Gotcha. Okay.
Yeah.
Thank you.
You're welcome. No problem.
Can you do another one?
What? So another reaction or something different? What do you want to see?
Wait, you said, I guess another reaction.
Okay. All right. Yeah. So we can do another one. So I'm gonna do this time. What I'm gonna do is a single replacement reaction because that's what I want to at least get to before we run out of time. I don't have a big enough eraser. All right, there we go. So let's say we have copper solid plus AgNO3 aqueous yields Ag solid plus CuNO3 2, and this will be aqueous. So there's 2 elements right off the bat that you can knock out very easily. Copper on the left, 0. Silver on the right, 0. Because they are in their elemental state. They're by themselves. Now what we're going to do is we're going to figure out the charge of silver, and we're going to figure out the charge of copper. Silver, all right, so the NO3 compound, nitrate, is -1. So that means silver is going to be +1. So we look at the copper nitrate on the right-hand side, and the nitrate itself is -1. Now the whole thing is equal to 0 because there's no charge. So there's 2 of the nitrates. That gives me -2. What cancels out -2? +2. So we look at the copper. There's only 1 copper. That means that 1 copper has a charge of +2. So the copper goes from 0 to +2, and the silver goes from +1 to 0. So copper is reduced or oxidized.
Oxidized.
Okay.
Oxidized?
Exactly. Yeah, it's oxidized. What does that mean? Silver then?
Reduced.
Yeah.
Stop.
Yeah. Good. Good. So in this video, we are going to be looking at single replacement reactions. Single replacement reactions are just known as displacement reactions. So when we talk about what it means to be single replacement, what we have to understand is that looking at the generic equation, we have A plus BC. Now A is going to be replacing B in this example. And so the products end up forming our AC plus B. And what you notice is that the reason why we call it single replacement reaction is because there's only one element that's being replaced. Single replacement. Now, there are different types of single replacement reactions. There's metal to metal, which is the example that we have up here. There's halide to halide, and then there's metal to water replacement. So we're going to be looking at just a couple of these over the next few slides. So before I get into that, when we talk about metal to metal replacement specifically, first thing we have to do is we have to use what is called the activity series. The activity series helps us to understand whether this reaction is going to take place or it's not going to take place. Now, in the case of the activity series, lithium is the most active metal on this chart and gold is the least active. The more active you are on this chart, the more likely you're going to be oxidized. And so normally the element that's going to be oxidized is going to be the more active element, and it needs to be the most active in the case of the reaction in order for it to occur. And so the higher you go up, the more active you're going to be. And so as I go back to this previous slide, A is the metal that needs to be most active. In fact, it needs to be more active than B, because normally C is your non-metal. We don't worry about C. C is just a tag along. So it's the reaction between A and B, and A must be more active than B in reference to the activity series. So this is a chart that you ought to have handy anytime you're working with this type of reaction. Now, to give you an example of one, this is where we take copper solid and we react it with silver nitrate, and this is in solution. Now what we need to do is we need to understand that this is A, silver is B, and then NO3 is C. Now what we need to do also is, once we understand that this is a signal replacement reaction, we need to go back and look at the activity series. Now the activity series will show to us that, so we've got copper here and silver is below. So what the activity tells us is that copper is higher on the chart than silver. Now copper, being that it's this A in this case, copper needs to be more active than silver, so yes, this reaction will occur. So copper is in the right placement on the activity series. So what will happen is the copper will replace the silver. And so you're going to form copper nitrate plus silver solid. So now our next question is, when these reactions take place, we need to focus on the oxidation state. So silver is +1, nitrate's -1, and then the elements that are by themselves are 0. Now the one element that we do not know that we're going to go look up on the activity series is copper. So when you look at copper here, copper is going to form a +2 charge. So when we go back over here, we need to make sure that this is +2. Now that also ties into balancing the equation. So nitrate is -1. So you need there to be 2 nitrates. As we see, the copper changes from 0 to +2. The silver changes from +1 to 0. So when we talk about which is reduced and which is oxidized, copper is oxidized and then the silver is reduced. So we talked about the activity series and the fact that the higher up you are on the activity series, the more likely you are going to be oxidized. So it's really important that you understand that the element that is more active, in this case copper, is the one that's going to be oxidized, and then silver is going to be reduced. And that's typically the way it's going to work with these types of metal to metal replacement reactions. Now below you'll see that that we have this final equation. Now this is your net ionic equation, just like what we see in your double replacement reactions where you figure out the spectator ions. The single replacement reactions also have spectator ions. In the case here, the spectator ion is nitrate, and so that leaves you with copper solid reacting with the silvers, and so and that forms the copper plus 2 along with the silver solid. So keep in mind that yes, you can write the ionic equation for a single replacement reaction. You just have to figure out the spectator ion. Remember, the spectator ions are the ions that are common. Now, if we rearrange this equation around, so instead of having copper solid as the beginning, so now if we started off with silver solid plus the copper 2 nitrate, and we look back at the activity series, we find that silver is below copper. And so remember that the element that is by itself has to be more active. In this case, silver is not more active, so we have a no reaction. In fact, you don't even need to worry about writing this. All you need to do is write no reaction. And so that's why it's so important to pay attention to the activity series. So looking at a couple other problems here. So here we have sodium solid plus calcium hydroxide. Now sodium is your element that you want to look at, and you want to figure out, is sodium higher than calcium? So going back up to the activity series here, we see that sodium is actually below calcium. So sodium is least active, so therefore this will be a no reaction. Looking at the next one here, we have iron 3 chloride reacting with zinc. So now we need to look to see if zinc is more active than the iron 3 chloride. So zinc is here, iron is below it, so yes, this reaction will take place. The zinc is more active, so therefore it's going to replace the iron here. And so you're going to form zinc chloride. Now remember, zinc is plus 2 on the periodic table, and that means you're going to have 2 chlorines. And then you're going to form iron solid. So balancing this equation out, we need to have, put 3 here, put a 2 there. This needs to be 3. This needs to be 2. Okay, so we're balanced. So next thing we're going to do is figure out which elements reduced, which elements oxidized. To do this, we're going to figure out the oxidation state. So iron is plus 3. There's 3 chlorines. Charge of chlorine is -1, so it's -3. Plus 3 cancels out -3. Zinc is 0 on the reactant side. On the product side, zinc is plus 2, and then iron is 0. So iron goes from plus 3 to 0, and then zinc goes from 0 to plus 2. So therefore iron is reduced and zinc is oxidized. If I were to write the ionic equation here, the chlorine would be your spectator ion, so you would end up having Fe plus 3 plus 3 zincs. And you always need to keep your equation balanced. Plus 2 iron solid. So this would be your net ion equation. So that's what you deal with metal-to-metal replacement. Now what happens when you have halide to halide? Well, it's just like it says, halide to halide. So this is where you have a chlorine reacting with HBr. So you have to have an activity series to figure out if this is going to actually react. And so the activity series here is this. So the higher up, and this actually comes from the periodic table, by the way. Fluorine's higher, chlorine, bromine, and then iodine. And this is I2. So in this example here, we look at chlorine. The chlorine is by itself has to be more active than the bromine, because it's halide to halide. And so it's not metal to metal, it's halide to halide. So that's going to replace the bromine. So chlorine is more active than bromine, and so therefore it will replace it. And so you are going to have a reaction. You will form HCl plus Br2. So balance this out, put 2 and 2 there, and that's it. All right, so that's all you have to do here. In this example, the hydrogen would be the spectator ion, but I wouldn't say you need to be concerned. The ionic equation really refers back to metal. You could do it for this one, but we typically don't worry about that. So Let's look at another one here. Let's say we have iodine. Iodine's a solid, by the way, in its natural state. So this is solid, liquid, gas, and gas. So let's say we have this reacting with HF. All right, so we need to figure out, is iodine more active than fluorine? Looking on the chart, no, it's not. So this would be a big NR, so no reaction. So there was another type of reaction which was metal to water. So I'm going to do a real quick version of this here. So this is a good example where you have sodium reacting with water. Now I'm going to write water as HOH because it's a little bit easier to see it here. So this is going to be a metal replacing the hydrogen. So the sodium needs to be more active than hydrogen on the activity series. It is more active. So you're going to form sodium hydroxide plus hydrogen gas. And so this reaction, you see this, you hear people talk about it. If you drop sodium metal into a pond, it will blow up. I don't suggest doing that, but it happens because of the type of reaction. It produces hydrogen gas, and it produces a whole lot of heat at the same point in time, and it just reaches the flash point and blows up spontaneously. So look up alkali metals, Brainiac. So Brainiac, alkali metals on YouTube, and they do a really good video of showing how the different alkali metals reacts with water as you place them into it. So thanks for watching, guys, and again, shoot me a comment or email and I'll be glad to answer any questions.